Pluto's circle crosses that of another planet. Pluto, the baffling little planet at the external scopes of our nearby planetary group, is working up fervor on the planet of space science. Ongoing reports indicate a conceivable encounter with Neptune, raising worries among researchers and space fans. Prominent figures like deGrasse Tyson and Michio Kaku have sounded alerts about the ramifications of this astronomical event. But how did Pluto end up on a crash course with its adjoining planet, and what could this celestial conflict mean for life on Earth? Join us as we unwind how something gigantic just crashed into Neptune and how researchers have been left stressed by this enormous irregularity. Pluto, once hailed as an undeniable planet, went through a change in its status, being renamed as a dwarf planet due to its exceptional orbit. Regardless of this downgrade, Pluto still charms and interests the galactic community. Later, expectations from respected researchers like deGrasse Tyson and Michio Kaku have raised concerns about Pluto's trajectory possibly meeting with Neptune, indicating an approaching string of crashes between the two heavenly bodies, which could have significant repercussions for Earth. Pluto's journey around the Sun stands out because of its unique attributes within our planetary group. Its orbit is unusually extended, crossing a stunning 2,048 years. Since its discovery in 1930, Pluto has yet to complete a full revolution around the Sun. Adding to its persona is the highly stretched state of its orbit, a flight from the more circular paths followed by the major planets. Besides, Pluto's orbit veers off by 17 degrees from the ecliptic plane, giving its path a more extreme grade compared to other planets. The combination of Pluto's nature and its curved orbit presents layers of complexity to its orbital pattern. One outstanding aspect is its occasional convergence with Neptune's orbit. For about 20 years during each cycle, Pluto ventures closer to the Sun than Neptune, opposing expectations based on their separate positions in the nearby planetary group. Diving further into Pluto's orbit, it's fascinating to note that it's not a perfect circle but rather an extended ellipse resembling more of an oval shape. This unique orbit results in significant variations in Pluto's distance from the Sun throughout its journey. At its closest approach, Pluto goes within around 30 astronomical units, AU, of the Sun, while at its farthest point, it reaches more than 49 Australian dollars away, twice the distance of Neptune from the Sun. Also, Pluto's orbit is inclined at a significant angle relative to the orbits of the major planets in our planetary group. This inclination not only adds to the complexity of its orbit, but also plays a significant role in its interactions with other heavenly bodies, especially Neptune. When Pluto encounters Neptune, their gravitational influence alters their trajectories. Over time, the complicated dance between Pluto and Neptune highlights the dynamic nature of our nearby planetary group. While Pluto was once viewed as a solitary drifter in the outer reaches, its close encounters with Neptune underscore the interconnectedness of celestial bodies, each exerting gravitational forces that shape the paths of others. In recent years, advancements in observational technology have allowed astronomers to track Pluto's movements with great accuracy. This has led to a deeper understanding of its orbit and its potential implications for the stability of the outer planetary group. While the likelihood of a direct collision between Pluto and Neptune remains low, the possibility can't be altogether dismissed, prompting continued monitoring and study by the astronomical community. Despite its modest size and distant location, Pluto continues to command attention and interest among scientists and enthusiasts alike. The question arises, why hasn't there been a collision between Pluto and Neptune? The answer lies in the gravitational pull from other planets. Astronomers began studying Pluto's path shortly after its discovery, and its trajectory perplexed them. Unlike most planets that stick close to the same plane as they orbit the Sun, called the ecliptic plane, Pluto stands out with its steep angle and oval-shaped orbit. The mystery deepened when they realized Pluto's path crosses Neptune's. Despite these complexities, Pluto's orbit remains stable, demonstrating the intricate mechanics of space. Understanding how three celestial bodies move and interact gravitationally, like Pluto, Neptune, and the Sun, is a significant challenge. It's like trying to predict where they'll go based on where they start and how they pull on each other. For Pluto, this challenge reveals how its path, Neptune's path, and the Sun's coordinate all work together like a simulation. Terms like precession, libration, and the VSOP variation assists scientists in solving this cosmic puzzle. Simulation is crucial for keeping planets in their orbits. When Pluto crosses Neptune's path, it's at least 90 degrees away, keeping them from crashing. Libration ensures that when Pluto approaches Neptune or other large planets, it's well above their path, reducing the chance of a collision. The VSOP oscillation, named after scientists von Zeipel and Packer, figures out why Pluto's orbit seems peculiar but remains consistent over time. Despite the chaos in space, some patterns and rules keep things in order. These rules keep Pluto's orbit stable, preventing crashes with Neptune or changes in its path. The possibility of orbital chaos, showing how a celestial body's path is highly sensitive to where it starts, is well illustrated by Pluto. Even small changes in its position or speed can disrupt its orbit over a long time. Scientists use computer simulations to figure out how Pluto moves in space. These simulations use complex math to simulate how Pluto interacts with other space objects like Neptune. By tweaking these simulations just a bit, astronomers can see how tiny changes can alter Pluto's path. In the late 1900s, these simulations found something interesting about Pluto's orbit. Even though there are factors that should make it stable, Pluto's orbit can still be unpredictable. Just a small difference in where Pluto starts or how fast it's going can make big changes over many years. However, even with this chaos, Pluto's orbit remains stable for a super long time, like billions of years. This suggests that even though Pluto looks chaotic, its journey around the Sun follows a kind of pattern. Predicting what will happen with planets like Pluto, which have eccentric orbits, is hard. These systems are so unpredictable that it's challenging to know what will happen in the long term. Simulations help us learn about what could happen, but they also show us that we can't predict everything completely. Figuring out Pluto's orbit is important, especially when we consider if it could collide with Neptune in the future. This knowledge helps us understand better how our solar system works. Pluto's orbit teaches us that even though orbits that seem unstable can balance because of gravity and how things move in space, continuing to watch and study these things is essential for expanding our knowledge of the universe and our place within it. When we explore space, we discover that things can be strange, and Pluto's orbit is a great example of that. Eccentricism: Pluto's orbit isn't like those of other planets. It's more oval-shaped, which means it's not a perfect circle. Sometimes it even gets closer to the Sun than Neptune does. This can make things interesting because Neptune is also something else. Sailing along its path, there's a small chance that Pluto and Neptune could collide with each other eventually. Despite its odd orbit, Pluto manages to avoid Neptune most of the time. This is because of something called gravitational forces. Gravity is like an invisible force that pulls things toward each other. So even though Pluto and Neptune could seem like they're on a collision course, their orbits are carefully choreographed moves guided by the pull of gravity. Pluto's orbit teaches us that space is full of surprises. What seems chaotic at first glance can be a delicate balance of forces. By studying Pluto's orbit, scientists gain insights into the intricate mechanics of our planetary system. This ongoing observation and analysis are essential for expanding our knowledge of the universe and our place within it. Imagine if Pluto and Neptune collided. It would be an astronomical event, sending shockwaves through our understanding of the nearby planetary group. While we've made progress in understanding space, what's happening shows that we still have a long way to go. Focusing on what large planets mean for Pluto's path gives us valuable clues about how our entire nearby planetary group works. It shows us that where each planet is and how it moves can change the paths of other things in space. Although space is complicated, some top scientists are worried that Pluto could collide with Neptune. This makes them wonder why this could happen, even though it seems unlikely. Neil deGrasse Tyson, a renowned space scientist, has some interesting thoughts about Pluto. He believes that renaming Pluto as a dwarf planet, not a big one like Earth, is a step forward. He thinks we're constantly learning new things about how things move in space. Tyson sees Pluto's strange path as a sign that there's still a lot we don't know. He believes that the mysteries of space are so intriguing. He also knows that big events in space, like Pluto's renaming, get people interested in astronomy. Tyson wants to help people understand the cool and sometimes strange things about how space functions. He thinks it's important to discuss how space mechanics can amaze us. Tyson works with other scientists to warn people about the potential dangers of Pluto's unusual orbit. In the wake of concentrating on Pluto a lot, the fact that it could collide with Neptune one day makes him concerned. He says this could cause enormous issues for our entire planetary group. An accident between Pluto and Neptune would be an intriguing and serious event. It would release a lot of energy and could break apart Pluto. Pieces from the collision could fly around space and hit other planets and moons. Neptune could also feel the impact and change how it moves. Famous theoretical physicist Michio Kaku, known for his contributions to string theory and science communication, offers an intriguing perspective on space exploration. He firmly believes that understanding the fate of space travel and the relationship between celestial mechanics and theoretical physics can be gleaned from studying peculiarities like Pluto's orbit. Kaku considers Pluto's orbit to be a window into the future of space exploration. By grasping the complicated gravitational relationships and orbital dynamics of celestial bodies like Pluto, we can enhance future space missions, helping with safer navigation through the solar system, predicting potential risks, and planning missions to distant corners of our vast neighborhood. Kaku stresses that patterns gained from Pluto's orbit can be applied to exploring other heavenly bodies, providing a roadmap for deciphering remote worlds. He frequently highlights the deep connection between celestial mechanics and theoretical physics, emphasizing that the movements and interactions of planets, such as the gravitational dance between Pluto and Neptune, are rooted in fundamental principles of physics. Kaku's work in theoretical physics, particularly string theory, aims to unravel these principles at their core. He suggests that focusing on the complexities of celestial mechanics, like Pluto's orbit, can offer insights into the fundamental laws of the universe. Like Tyson, Kaku has also pondered the potential collision of heavenly bodies, relating it to his theories about the universe. A crash between Pluto and Neptune, while significant in astronomy, could offer a unique observational opportunity, potentially contributing to our understanding of string theory. String theory, which replaces point-like particles with one-dimensional strings, seeks to describe the fundamental forces and matter in the universe. Such a collision could create extreme conditions of energy and gravity, shedding light on the behavior of fundamental particles and forces under extreme conditions. Moreover, the gravitational waves produced by such an impact could provide valuable data for testing predictions of string theory regarding gravity and spacetime. While the direct impact on Earth would be insignificant due to our distance from the outer planetary group, the scientific implications could be profound. Understanding events like this could expand our appreciation of the fundamental nature of the universe as described by string theory and other theoretical physics areas. Pluto's unique characteristics, influenced by the gravitational forces of neighboring planets, especially Neptune, highlight the intricate and dynamic nature of space. Yet, the universe holds many secrets, and the three-body issue is just one of them. Scientists expect other potential calamities, highlighting the ongoing quest for understanding and exploration in the vast universe. Although it's highly unlikely, there's still a small chance of planets encountering each other in space. This can happen because planets' paths are influenced by various factors, like gravity from other planets, which scientists call the three-body issue. In places like the TRAPPIST-1 system, where there are 7 Earth-sized planets, the gravitational forces create a kind of dance in how the planets move called orbital resonances. Over time, these resonances can make a planet's path less stable and could lead to collisions. Although systems like TRAPPIST-1 are teeming with planets, collisions aren't happening right now. Scientists keep an eye on these systems to understand how planets affect each other's paths, especially when they get close. This helps us understand how planets move in space. Sometimes, there are rogue planets that don't orbit a star and float around erratically. These planets used to be part of a star system but got ejected due to things like gravity or when another star came too close. Over time, these wandering planets can go far and could run into other star systems. But since space is mostly empty, the chance of them hitting another planet is very low. Rogue planets are interesting compared to the number of stars and planets with stable orbits, so collisions are even more unlikely. When galaxies merge, it can disrupt the orbits of the star systems within them. Although planets probably won't crash into each other directly during these massive events, gravitational interactions can change how stars and planets move. Sometimes planets get flung out into space, becoming rogue worlds. Other times, they could collide with each other or their host stars. These disruptions might actually create new celestial bodies or make new stars. The late heavy bombardment hypothesis suggests that around 4 billion years ago, there was a period of increased collisions involving comets and asteroids. This bombardment is believed to have occurred because the outer planets, like Jupiter and Saturn, were moving around a lot, which disturbed the paths of lots of smaller objects in space. As a result, these smaller objects got thrown onto eccentric paths, many ending up in the inner part of our solar system. This led to a big increase in collisions on planets like Earth. While these impacts didn't involve planets colliding directly, they demonstrated the fact that gravity can make big changes to how things move in space. This bombardment shaped the surfaces and histories of planets in our planetary system and could have even brought water and organic material to Earth, helping to shape our planet.